Hello, my name is Don Metzger. This video is the second in a series of videos describing the use of the Analog Devices AD9084 being hosted by a Xilinx VCU118 board running under Analog Devices IIO software and being operated by Quick Systems Quick Transceiver software. The emphasis in this video is on calibrating the system for better RF performance. Here's an overview of the video. If you are just setting up your AD9084 system, I would recommend that you go to the previous video on YouTube called AD9084 VCU118 IIO Setup. That'll get you started. We assume that you already have your system running and are familiar with running Quick Transceiver. In today's video, we'll be talking about the board setup that we'll be using. We'll get you set up with the software, and then we'll do a 256 QAM transmit and receive, first at 2 gigahertz and then at 8 gigahertz. And we'll run into a bit of a problem when we are operating at 8 gigahertz. So we'll show how to resolve that using calibration using a chirp. And then we'll look finally at the signal quality improvement that we saw at 8 gigahertz. Here's our board setup, the same as before. Up at the top is the VCU118. Down below is the AD9084 eval board. Again, if you're just setting up your system, you should see the previous video for how to get the whole system running. We've removed all of the loopback cables except DAC 0 to ADC 0, and we're using an amplifier in that path because the output of the DACs is not full scale on the ADCs, and so we put a little Analog Devices ADL 8100 amplifier in that path to bring up the DAC signal level just a bit. Okay, so we've started up the Quick Transceiver program, and as always, I'll walk you through the setup. First of all, we want to make sure that we're talking to the right piece of equipment, 9084 being hosted by the VCU118 over the network at that IP address. We also want to be sure that we have the right settings for the instrument. We're talking DAC A0 at 2 gigahertz, receiving ADC A0 at 2 gigahertz, and we're doing 40,000 samples. The waveform that we'll be transmitting is a 256 QAM at 500 megasymbols per second, and the sample rate of the system is 2.5 gigasamples per second. And finally, just to make sure we're on the same page, here are the active windows that I'll be using for today's demonstration. The acquired waveform, the acquired spectrum, the acquired spectrogram. Then we're going to have the processing waveform, the final symbol constellation. We're going to have adaptive EQ coefficients and response, and the measured results. And we can just go hit the start button. Okay, so we are transmitting and receiving a 256 QAM signal at a 500 megasymbol per second rate, about a 500 megahertz occupied bandwidth, and we're getting an EVM of maybe minus 30 dB or about 3%. I'm going to go in here and turn on some adaptive equalization, see what that's going to do to clean up the signal quality. I'm going to give it 65 taps. That's one of the things we learned out of the first video, is 65 taps makes for a nice adaptive equalizer. And so you can see the final symbol constellation has gotten to be nice and tight. We've got an EVM around 50 dB down, or 0.3%, and this is the response of our equalizer and what it's having to do to take the input waveform and clean it up so that we get a nice final symbol constellation. That's working at a center frequency of 2 gigahertz. Let's move this up to 8 gigahertz now. So I'm going to go in and turn off the adaptive equalization so we can see what things look like to begin with there. For the 9084, I'll go in there and tell it do 8 gigahertz on the transmit, 8 gigahertz on the receive. And let's start that up. That doesn't look very good. I can see a fair amount of ripple across the band here. So we do have the amplifier that's helping us with signal level, but we're having a rough time recovering this signal. Let's go in and see if our adaptive equalizer can help us here. Maybe it can clean up things. Do the 65 taps. It did make it better, but EVM of 5% is not exactly what we're interested in. You can see lots of symbol errors up here, so we're going to be making lots of bit errors at this type of symbol rate. So the way that we deal with this problem is we first go back and do a calibration with some sort of a waveform. I prefer to use chirp waveforms because they can sweep the whole bandwidth of that we're interested in using. So I'm going to use a linear frequency modulation, a chirp, that's going to sweep 2 gigahertz worth of bandwidth, and it's a 2.5 gigasample sample rate on that. So I'm going to select that, and then I'm going to go to arbitrary waveform equalization, and I'm going to give it this file. This is the chirp only. The stimulus that we're using is a chirp and an off and a chirp and an off, but when we use the ideal waveform, we just want to focus on the chirp itself. So this is just the chirp part of that. I'm going to use 65 taps, and the time accuracy is going to be 1/8 of a sample, and the sample rate's 2.5 gigasamples per second. So we turn that on, and we click our button, and here is what our equalizer is coming up with. I wouldn't call this adaptive equalization. We call it arbitrary waveform equalization. I'll stop it here so it's not hopping around quite so much. You can see up here we're using this chirp waveform to sweep the entire bandwidth centered on 8 gigahertz from 7 to 9 gigahertz, that 2 gigahertz span. We're sweeping with the chirp, and here's what we're getting from this is the time domain view, and this is a chirp. So when it comes on, it's down here at the 7 gigahertz, and then as time plays out, it sweeps up, and you can see what's happening. There's ripple in there, there's a droop, there's a significant fall off. So we run this arbitrary waveform equalization, and it comes up with tap coefficients, and this is the frequency response of that. You can see a really big adjustment that it's having to do up here at the high frequency end. A lot of it has to emphasize stuff that's being de-emphasized in the actual response. But the sum of both of these together, the input and equalized, is giving us something that looks nice and flat like this. So I'm going to go to the Adaptive EQ Coefficients window and right-click on that and tell it to save these coefficients to a file. The display of these is just magnitude, but they're complex coefficients. You can display them any way that you want to. This is just a little file format that we came up with, text file format for saving complex FIR coefficients. So I want to call this DAC0 ADC0 at 8 gigahertz, just to keep straight what channels we're equalizing and what's the center frequency. Okay, so we've saved our coefficients. So let's go back to our original 256 QAM stimulus waveform that we've been using. So transmitter file, and let's choose that 256 QAM signal, and we're going to hop into PSK demod mode. Let's make sure that we are not doing any adaptive equalization at the moment. Okay, and start things running. So there's our familiar blob of output data here. I'm going to go into receiver waveform processing, and I'm going to turn on those complex tap coefficients and apply them to the received data. And boom, immediately things look a whole lot better. We're now getting EVMs maybe minus 41, minus 42, 0.7, 0.8%, something like that. So I would call this fixed coefficient, fixed calibration. We've used the chirp waveform to help us come up with calibration coefficients. Now we're applying it to the data, and it helps a lot, but we can still add adaptive equalization on top of it. So let's go in here, let's turn on our adaptive equalization at 65 taps and see we gained a few more dB by doing this. Stop this from hopping around so much. So we are now doing two levels of calibration and equalization. One is using those fixed coefficients that came from the chirp, and then we're doing adaptive equalization on top of that because we know what kind of signal we're using, and we can do a better job because it's a PSK QAM kind of waveform. So what have we seen in this video? We started at 2 gigahertz, and we saw that there was some ripple across the passband, but adaptive equalization could clean that up for us, and that we could get a good response. When we went to 8 gigahertz, there was too much ripple across the band, too much droop, just not a good response there, and so we had problems even with adaptive equalization in recovering the signal. And so we used a fixed calibration. You can use any waveform you want. I like chirps. I used a chirp and determined the FIR tap coefficients, and then we applied that to the 256 QAM signal and saw that we were able to get a good signal, and then we used adaptive equalization to just kind of clean things up, and we get a nice response. So basically we go from something with no information being conveyed, like on the left-hand side, that symbol constellation, to something on the right, which is really very good, despite the fact that there's a lot of imperfection in the system. And this imperfection is not focused on the chip, it's just an RF system. There are many components in there. There are balunds, there are launches, there are cables, there are traces across the board. There's just a whole lot of stuff there, and you're going to get imperfections. You're going to get these kinds of droops and things like that that need to be cleaned up. And fortunately, we can do that, and we can get a good response out of the system. All right, that's it for this video. As always, you can visit us online at quicksystems.com to learn about the Quick Transceiver software, or you can contact us by sending an email to sales@quicksystems.com. Have a good day.